some different qualities of sound. Okay, so we're gonna go through what properties of sound waves make one sound different from another, and then the Doppler effect, which is not really related, but we got to cover it. All right, in sound waves, guys, sound waves are produced one of two ways. Okay, the first way a sound wave is produced.
Is this a PowerPoint?
Yes, PowerPoint. I'm going to show you something under here. Sorry. Sorry. Okay, the first way a sound wave is produced, guys, is by vibrating solids. This is the most common way sound waves are produced. Okay, so your vocal cords, they produce sound waves by vibrating. A drum produces sound waves by vibrating. A guitar produces sound waves by vibrating. So let me give you a little drawing of how that works. If I can get this to pull up, please. Having all kinds of trouble today. Okay, so we'll start with the example of a speaker. If I have a speaker, y'all know that that's composed of a cone. And if you're watching the speaker when the music is going, the cone's doing what? It's kind of vibrating back and forth, right? Okay, so for a little bit, if I were to slow that down many times, for a little while I'd see that cone move this direction, right? Okay, well when it moves that direction, all the air particles in front of the cone get pushed together, right? So in other words, that creates a compression, okay? Then it's going to not do that. It's going to move back the other way. Okay, well when it moves back, now there's kind of an empty space in front of the cone. Okay, which is creating a rarefaction. Then it moves back forward, which creates a compression. So you see how those compressions and rarefactions are in waves moving away from the speaker. Okay, that's why anything that vibrates creates sound. Okay, by moving back and forth and creating compressions and rarefactions. All right. So another example of something that does that is a tuning fork. Tuning fork. And a tuning fork always produces the exact same sound. This tuning fork right here is at 480 hertz. You can kind of see it's written on there. So what that means is every second it creates 480 compressions and rarefactions. Okay? And so think the way this one does it. If I take the tuning fork and I strike it down, okay, then this gets bent in. Okay, that gives it EP, right? Okay, that's going to make it go back here and vibrate back and forth. When it goes this way, it takes air particles over here and it compresses. So when it goes that way, I get a compression. When I go this way, it creates a rarefaction. It goes back and forth, compressions and rarefactions. Okay, so okay, when I hit that, you ought to be able to see that it is indeed vibrating. Okay, when I stop it, you can see that it's not vibrating now. It is vibrating then, and more dramatically. Yeah. Okay, so it is indeed vibrating very rapidly. Okay, so that's the first way that sound waves are created. The second way sound waves are created is by expanding or contracting liquids and gases. Okay, so a solid is not really required to make a sound. Okay, a gas can create a sound in and of itself. Okay, so examples of that would be an explosion, a cannon firing, a lightning strike. Okay, all those would be examples of an expanding and contracting gas producing a sound wave. I guess I can give you a drawing of how that works too. I guess. Let's say I have a gas and it's occupying this space. Okay, and so we're assuming it's not in space, so there should be a certain volume of gas around that as well. So we'll give a certain volume of gas around that volume of gas. If this volume rapidly expands, so maybe it's going to expand to be this size. Okay, if it rapidly expands, then this outside, that gas outside of it gets rapidly compressed. Y'all see that? Okay, so that creates a compression of a sound wave. Okay, well, I mean, it's not going to stay expanded most likely. Okay, most of the time what happens is this gets heated, it expands because it gets heated, and then after it's not going to stay hot, so it's going to contract again. Well, when it contracts, now this is a compression moving out, so I'm going to be left with a rarefaction. Okay, so that's what happens in an explosion, and that's the explosion you saw up there. Bam! That gas rapidly expanded. Okay, and I saw that area of condensed air that was around the compression, and then there's a rarefaction after that. Okay? So lightning does the exact same thing. When lightning strikes, that's my best cloud. Okay. When lightning strikes, the air that is conducting the electricity rapidly heats to above the temperature of the surface of the sun. Okay, I mean rapidly, and I mean, who in here has ever seen a slow lightning bolt? Okay, I mean it's rapid. Okay, so instantly we go from being 70 degrees Fahrenheit to 10,000 degrees Fahrenheit. Okay, so that rapid heating, who in here says that rapid heating causes air to condense and get smaller? That answer's no. No one. Okay. No, that rapid heating causes it to expand. Okay, so that creates a what? A compression. Okay. Okay. Has anybody in here ever heard a lightning bolt really, really close up? Okay. When it's close up, you notice it's not like a rumble when it's close up. I mean, it's like, I mean, and it's not a lingering sound either. I mean, it's like boom. Like, okay, it's kind of like an explosion. Okay, why do you think it sounds like a rumble when it's far away? Because there's some echoes involved. Okay, so you might be hearing that lightning strike echoing off 15, 30 different things. Thunder is just the sound created by lightning. Mm-hmm. So have y'all ever heard the old adage, when you see a lightning strike, count 1 Mississippi, 2 Mississippi, and however long it takes for you to hear it, that tells you how far away it is? Okay, well the light from the lightning is traveling towards you at 3 times 10 to the 8th meters per second. And the sound is traveling at 343 meters per second. So obviously the light gets to you way before the sound. So if you just use the equation V equals D over T with the speed of 343 meters per second and the time of whatever you get, then that'll tell you the distance of the lightning from you. Okay? So as that time is decreasing, you know the storm is moving towards you. And as that time is increasing, you know the storm is moving away from you. Okay? Just random little tidbit there. Okay, so that's the 2 different ways sound can be created. There's 2 aspects or 2 characteristics of sound waves that I want us to discuss today. The first characteristic involves how loud the sound wave is. Okay, so the difference between and ah. Okay. Same sound, just different intensity or different loudness. Okay, and that's going to be related to the amplitude of the sound wave. Somebody, how do you visualize amplitude in a sound wave?
The wave.
What's the difference between a high amplitude sound? Let me just pull it up. Let me just pull it up. I have two different sound waves here, guys. Which one's louder, the top one or the bottom one?
The bottom one.
The bottom one. Why?
More compression.
You see, it's just more compressed, right? Okay, so the bottom one's higher amplitude, so that would be a louder sound wave. Okay, notice how those compressions are in line. That would be making the exact same sound. Okay, so that would be the difference between. Give me a second, let me pull it up. I have a little frequency generator here. Ooh, no, we don't want them there. No.
We don't want to hear that.
What was that mosquito thing?
Okay, that's 500 hertz. Hear the difference? I mean, the difference there is just volume. This volume might be the top one. That might be the bottom one. Okay? So those compressions and rarefactions are still lined up, just different volume. Oh,
Thank you.
quit your complaining. It's going to come back. Don't worry. It's going to come back way worse than it is now too. So just prepare yourself.
You gonna make it louder?
Yeah. Different pitch. Okay, the second characteristic of sound that we need to be familiar with is the frequency. And that tells me how high or low it sounds. Okay, so the difference between ah and ah. Okay, those sound different. Those are about the same volume. Oh, thank you. Those are about the same volume to me. However, they just sound different. And that's kind of hard to describe. You know, we say higher or lower. I don't really know what higher means. That's kind of hard to describe the difference between those two. Okay, but the word we use is pitch. Okay, and the difference between those is the frequency. Okay, so when I was looking at those previous pictures and I saw those lines, okay, remember the compression lines, and a high pitch, okay, those would be really close together. And a low pitch, they'd be far apart. Okay? That makes sense? So if I'm drawing out the wave, and I'm going to use the wrong but kind of right, but kind of wrong way, okay, this would be, that would represent a low sound, and this would represent a high sound.
Yeah.
Notice the same amplitude. This is just more frequency. Well, now this would be compressed dots. This would be spread out. Compressed, spread out. So this would be compressed, spread out. Yeah. How often you're getting the compressions?
So that's why low sounds are much more.
What now?
Low sounds are less loud.
No, they're not less loud. They're just different. Okay. On average, guys, humans, we can hear a frequency range of about 20 hertz to about 19,000. Some students can hear above 19,000. Very few. And we'll go through and do a little test here. One general rule, guys, with frequency, every time you double the frequency, you go up an octave. Okay, so this is 500 hertz. Okay, if I make that 1,000 hertz, double the frequency, I go up an octave. Okay, double it again to 2,000, that goes up another octave. Okay, so that's 125. That's 62.5. I don't think those speakers can make 62.5.
Oh wow.
That's 10,000.
Wait, I can't hear anything.
I'm gonna move us up to 15.
I can hear that a little bit.
That's 15,
It's sharp. Ouch.
16,
It's like being stabbed in the ear.
17. I'm lost at 17. I can't hear that.
What is
It's like being
this?
stabbed.
Wait, what is this?
Huh?
What's
You don't hear that?
This is 17,000.
Can you go up?
This is 18,000.
Still here.
And so
I can hear I can only hear my right ear go.
that's 19,000.
I can hear that. I'm done. I've been shot.
Nope. Can you?
Okay, I'm going down to 10 so that I can make it 20. That's 20.
How do we know you're not just kidding?
No, you can come look at it if you want to.
Talk to a machine and like make it put out.
Yeah, I can.
I suppose you could. Okay. But no, still on. Yeah, that's off.
Yeah.
It's like irritating. So I don't know if I can hear it or not.
Yeah.
My ear is like irritated. So
Yeah.
that's it.
Okay, so that's the frequency range for humans. Sounds can be above 20,000 hertz. Obviously, I mean that was making a sound wave that you couldn't hear.
And then go below 20.
The speaker.
Yeah.
No. That speaker probably can't go to 50. But so it would be possible for us to hear something above 20. You have to slow it down. Because you know the old records how you could adjust the speed, and so it would be like this if I was talking slow, and as I try to talk faster, it would go higher now. You know what I'm talking about? Like as you sped up and go higher. So if you took something that was really high pitched and slowed it down, you'd be able to hear it.
What's that app called? Frequency.
That's a frequency gen. I don't know what it is. So hertz measures the pitch. We're going to measure loudness. I don't know why is that not showing up right? Well, whatever. We measure loudness of a sound in a unit called a decibel. I don't know why it's lowercase d, capital B. I don't make it. And so on the decibel scale, guys, first of all, 0 is the minimum a human can hear. So you can have negative decibels. That would just be a sound that was too quiet for a human to hear. Okay, but we look up here, 40, we have raindrops. 90, a hairdryer. In the hallway, typically during class change, it'll get about 80. 105 rock concerts. Notice 115, an iPod at maximum speaker volume. I've read that an iPod, if you're listening to it at 100% volume, can cause permanent damage in under 10 minutes. The longer you listen to something at higher decibels, the less time you can listen to it and it be safe. Okay, so up here with gunshots and fireworks, I mean, you wouldn't want to be listening to something, a gunshot. Just take the sound and play it constantly for an hour. You might not be able to hear by the end. A blue whale, I read, can create a sound at 180 decibels. And it's capable of that sound is capable of traveling for miles.
How loud can a human go?
It depends on the human. I don't know how loud the loudest human is. All right, guys. On the decibel scale, a 10 decibels. Every 10 decibels represents 10 times louder. Okay, and that's from 0. Okay, so 10 decibels would be 10 times louder than 0. 20 decibels would be 100 times louder40 decibels would be 1,000 times louder than 0. 40 40 decibels, 10,000, 50, 100,000. Okay. That's fine. And decibels, guys, are based on pressure changes. Okay, a 10 decibel increase in volume is represented by 0.001 pascals. What is atmospheric pressure? What is atmospheric pressure? 101, 325, right? Okay, so since atmospheric pressure, guys, 101, 325, a 10 decibel sound would undulate between 101,325.0001 pascals and 101,324.9999 pascals. Okay, that's that tiny bit of pressure differential that you would get from a 10 pascal, from a 10 decibel sound. Okay, which is kind of incredible to me that the ear is capable of detecting the difference between 101,325 pascals and 101,325.0001 pascals. And not only can it detect it, but that's 10 times louder than the minimum sound we can hear. So the ears are pretty incredible, and if it's a 1,000 hertz sound, then your ear is vibrating at 1,000 times per second and picking up 0.0001 pascals of pressure. So that's pretty incredible. We got volume and frequency. Clear. Okay, Doppler effect. I'm going to explain the Doppler effect with a sound. Okay, you ready? This is an appropriate thing. No, it's not going to hurt. Okay, you ready? Got it?
Yeah.
Doppler effect? Okay. So, Doppler effect, guys, is a perceived change in the frequency of a sound wave. In other words, it sounded like this, now it sounds like this. Okay, beep boop. Okay, so for an example, guys, let's say you're waiting at the train stop and a train passes by. I don't know if y'all were aware when Clinton used to have the trains going. And if you're sitting there waiting, you hear okay. Is the train making a different sound just because it passed you? No, okay. It's just you're hearing it differently. Okay, and that's due to the Doppler effect. Okay, the Doppler effect, guys, is caused by the compression and stretching of wavelengths. Okay, so to put that into an image, if the little bright spot in the middle is moving to the left, I'm trying to think of the video, if that'll be to the left. Yeah, to the left. Okay, if the bright spot is moving to the left, then you see on the left the wavelengths are shorter. They're smaller. What does the small wavelength do to the frequency? It increases it. So up here it sounds like right? Okay, back behind it, it's moving away now. Those wavelengths are stretched. So that would sound like So if I'm an observer and this thing is going past me, I'm hearing You want me to do it again? One more time? No. That makes sense? Okay, just to kind of walk through and explain what's causing that, I'll use the example of a race car. And I'm going to draw you my best, most elaborate race car. Okay, So yeah, it's a good one.
Is that also the straightest road you've ever drawn?
Yes. There you go. So let's say this race car is going in this direction. Well, let's start off. Let's say it's stationary. Let's say it produces one sound wave, and the sound wave has had some time to move, and so now it's out there. And so it's going, it keeps on producing sound wave because it's running. Because what we would see is that the same amount of distance over here as there is over here, right? Because it's not moving. And eventually, this sound wave would occupy the exact same space as that one did, right? They're going to do the same thing. But if that race car moves, it produced this sound wave. So that sound wave is exactly the same. Okay, however, now it's moved over in this direction. So by the time it produces the second sound wave, it's in a different position. Eh?
Are you saying the first one still exists?
Yeah, the first one's still moving out. But when it produces this second one, it's a little bit closer to this side of the first one than it is to that side of the first one.
That's why on the wider side it's going to sound lower.
So on this side, my wavelengths are stretched, but on this side, my wavelengths are compressed. Huh?
So on the left side it would be
Mmm.
louder.
Is this forward? No.
No?
It would sound higher.
Not louder, higher.
Okay? The same thing happens even, let's say the thing that's making the sound or the producer of the sound is staying still, but the perceiver is moving. So let's have the example. Maybe I have a weather siren. Okay, so it's sound waves. There's no Doppler effect if you're sitting still. And let's say you're walking in this direction. Okay, if you're walking in that direction, you're walking into the sound waves. So do you agree, there should be a certain amount of time before this one hit, there should be a certain amount of time between these two sound waves hitting you, right? When I say sound waves, I mean compressions, okay? But if you walk in this direction, then you're going to hit this one sooner than you should because you move toward it. So in other words, the frequency over here is going to be higher because you're moving toward the sound waves. However, over here, if I'm moving in this direction, I'm moving away from them. So this sound wave's kind of chasing me. So it's going to take it longer to get to me. So my frequency over here is going to be lower. So as I drive past that siren, I hear... That's my siren.
That's nice.
This is kazoo.
I thought that was
As you drive past this kazoo... That makes sense? Okay, so general rule for Doppler effect, guys. General rule, if an object is heading towards you, or if you're heading toward the object, if the distance is decreasing between you, if you're getting closer, then it sounds higher.
Why do tomato sirens and like ambulance sirens, like the pitch is like wavering? Is there a purpose for that, or is it just that it'll stand out?
So it'll stand out. They're actually wavering the pitch.
Right, on purpose.
Yeah.
If it's standing still, it still goes.
It's just kind of boring, don't you think?
Huh?
It's just beep, that's kind of boring. Also they differentiate between this is a police siren, this is an ambulance, this is a fire truck. They all sound different.
I hate the lights.
Yeah, I know.
Yeah. Them things too bright, man. People can't see because of the light.
All right, back to Doppler effect. The opposite is true, guys. When an object's moving away from you, okay, it's going to sound lower. All right, here's my equation. It's going to take us a second to walk through the equation. This does go on the equation sheet. It will be number 37. You can put this under Doppler effect. And you may put those two notes that are below the equation. You can put those on your notes section. Okay, let's walk through this. F, we said D is for the detector. That's the listener. That's whatever's hearing the sound, whatever's picking up the sound. Okay, S is for the source. That's wherever the sound is originating. That could be from an echo. It doesn't matter. It just wherever the sound's coming from. Okay, whatever is producing the Doppler effect. Okay, so this is the frequency heard by the detector. So if you're in a car and you're listening, then you're the detector. Okay, the frequency heard by the detector is equal to the frequency produced by the source. So if you're driving by a weather siren, that's where that would go. Okay, if the weather siren's at 60 hertz, that's stupid, 600 hertz, then that would go there. Okay, times the speed of sound in air, that's 343, minus the speed of the detector. Okay, how fast you're moving if you're listening. If the detector's sitting still and the source is moving, then that's 0.
Well, aren't
Okay.
you the detector?
But now,
Yeah, you are the detector, right?
well, I mean, you could be producing the sound, but generally you will be the detector. Okay, divided by the speed of sound, 343, minus the speed of the source. If the source is sitting still, that's 0. Now let's talk about negatives and positives. If the two objects are approaching, the velocities are positive. If they're moving apart, the velocities are negative. Okay? Huh? Okay, grab a partner. Talk it out. Hmm?
I'm asking
It is a lower, stretched out, longer, lower,
What's this?
smaller.
Is there such thing? Yeah.
If they're both going this way, then
You just make this positive, this direction positive?
yeah, they just both be positive. Or both be positive or both be negative.
One is this, one sounds lower. You know about it's approaching you. It's on the other side of you. It's like, here's the horn. Okay, you are stationary, but the train horn is
Can
coming
you
to you.
explain the
So
third one?
first it's like,
That's a bad question.
Yesterday you said
yeah,
that
it's
sound
supposed
waves
to
go
go
high
away,
and carry sound waves.
it's apart.
Yesterday
Way
you told
we
me. Well, that was a bad.
Because the way
That was
we
a trick
close
question.
together,
So
which means
solids
it's a
do
louder
carry
sound.
sound waves,
Or
but they
higher
don't
pitch
carry
sound.
this
Like,
compression wave because
yeah,
solids don't
like
compress
a
very
one.
much. So typically
Like it
solids
says,
carry them as
How do
transverse
solids
waves.
carry sound waves?
And then that transverse wave gets created back into a compression wave the same way that
Oh,
a
vibration.
tune, just like a tuning fork picking up a compression wave, turning into a transverse wave, and then making that back. Alright, number one, guys, what effect do you think the wavelength has on a sound wave? As the wavelength gets bigger, the sound is going to sound lower. Okay, if the wavelength is longer, it's going to sound lower.
Okay.
Okay.
You should say that.
Huh?
That's higher.
It's gonna sound.
You should say that.
Well, the higher means higher, lower. Number two, a train horn is off in the distance, and you hear it. A train is off in the distance, and you hear its horn. You have an identical horn next to you, and you blow it. The distant one sounds lower. What do you know? It's moving away from you.
Oh.
Okay. It's creating a lower sound, so it's moving away from you. Then number three, I don't really like that question, so we're going to skip it. Okay.
What's the answer?
Solids typically carry sound waves in the form of transverse waves, and then they transfer that transverse wave back into a compressional wave when it hits the air. So kind of in the same way that this is a solid, and it carries the sound wave as vibrations, like literal movements, vibrations. Okay, this would be more like a transverse wave, and as opposed to a compression wave. Okay, let me do one example because we're running low on time. Give y'all a second to read that. Police cars use radar guns to detect the speed of oncoming cars or outgoing cars. And a radar gun, essentially all it does is it fires a sound. Okay, that sound echoes back, and then it says, does it sound different? Okay, if it sounds like a different sound than they fired out, then they know that the object is moving. Okay, and then, well now?
Is there like things called sound deflectors?
Sound deflect. Are you trying to avoid radar guns? No. Okay. Well now?
I was gonna say, does he want to install one in his car?
Yeah. Well, they do have those, but they're typically on airplanes, and airplanes that are meant to avoid radar, and they're millions of dollars. So I would probably just give up on that dream. Okay. So the police car shoots out 35,000. So that's going to be the source. Okay, so that's FS. I know y'all can't see what I'm writing right now, but I'm gonna pull it up in just a second. So FS is 35,000. Okay. The police car hears 39,600. So that's FD. Okay. It's looking for how fast the car's going. That's going to be VS. And since the police car is stationary, that's the detector, that means VD equals 0. Okay? Okay, so my equation, FD equals FS times V minus VS over V minus VD. Wait, it's V minus VD over V minus VS, right? I got that backwards. Okay, so since the police car is stationary, VD is 0. I'm solving here for VS. That's going to be kind of a pain.
You can't see that one.
Oh, sorry.
Yeah.
It's going to appear in 5 minutes.
Do you iron the paper?
Oh,
Okay.
I think
What was wrong with the marker you were using before?
Shh. It's just kind of hard to write with because it's so thick. Okay, so I'm looking here for V S. Okay, that's going to be kind of a pain to solve for. To me, the easiest way to do this is going to be to okay, you're going to multiply both sides by V minus V S. Okay, so I get V minus Vs times Fd equals Fs times V. I'm solving for Vs, so I'm going to divide by Fd now. So V minus Vs equals Fs times V over Fd. Subtract V from both sides. And then, take the whole thing and switch it because that's negative. Okay, we're out of time for me to actually write down plugging in the numbers, guys. But this is 343 minus Fs, that's 35,000, times 343 divided by 39,600. And so the speed of the car is 39.8 meters per second. What now? We're going to do that tomorrow. Don't worry about it. Okay, so that's how police cars detect your speed. They hear a different sound coming back, and they use calculations. Well, the computer does uses calculations to get that speed.